Okay, welcome back everyone. Is it time? It's time. German, strict. Who of you has heard, let's plunge into the deep waters. Who of you has heard of the dimensionally extended 9 intersection model? No. Well, this is a cool, quite cool, result of whatever it is, computational geometry or geographic information science or whatever these people tend to think about. It's an intersection model, right? We have geometries, points, lines, polygons, they can intersect. How do we encode different forms of intersections? Well, here is the idea. We can have like two objects, A and B, and then A and B both have an interior, they have a boundary, and they have an exterior, right? Those are three properties. Of course, if you have a point, it's a little bit abstract what the interior is. But anyway, they took care of it, right? Think of polygon, interior, boundary, exterior. And then the other object also has an interior, boundary, exterior. And then you can look at all the combinations of these three, right? In this intersection, like it was drawn here, we see that the interior of A and of B have intersection here, the red area. And that red area has dimension 2, meaning it's an area. It's a two-dimensional thing. The interior of A and the boundary of B here form this line. Yes, this line has dimension 1. It's a line. Yes. Interior of A and the exterior, again, are this red area, have a dimension of 2. So you get all the 9 combinations of interior, boundary, exterior of the first object, interior, boundary, exterior of the second object, and their intersections all have a dimension, 0, 1, or 2, or they do not intersect, and then we call it false, yes, not present. And that gives us a string, and that is this string here, that consists of 9 characters, in this case 9 digits, that can look like this, right? But as I said, sometimes these things are also non-existent, and then we call them false. And we can sort of also say they are true, in which case it has to be 0, 1, or 2, meaning it intersects. So true means there's an intersection, false means no intersection, star means anything. And by that model, basically, we end up in defining all the predicates, yes? Here equals, disjoint, touch is contained, we see all these familiar predicates, and they are all defined in terms of a particular pattern with wildcards, right? With these stars in it. And so these are basically all our predicates, all our words, but defined then in how interiors, boundaries, exteriors of two objects intersect or not, and this is useful. So that leads to these 8 or 10 categories that are defined in the single features standard. So they are defined this way by this intersection model. This is a model. There are also other models, simpler models that don't look at exteriors, for instance. But we can also do more with that. For instance, we can look at whether two geometries intersect in a point or whether they intersect in a line, right? In both cases, they touch. Yeah? Two counties can either have a common boundary or they can have a common point, and then they touch. So this is if you have like gridded data and you do neighborhood models, you either define for a grid cell, you either look at the north, east, west, south borders, so the 4 borders that the rook can move, the rook neighbors, or you look at the 8 borders, right? If you do autoregressive models or something like that, you have to define what are my neighbors. And you can say, well, touch, meaning 9, or you can say, no, they have to have a line boundary, a one-dimensional boundary, meaning rook neighbors. Yeah, there's 2 kinds of neighbors. And they are not in this list, but if you can basically say, well, I'm going to select intersections based on, based on this string, then you can do everything. And that is actually what ST relate allows you to do. That is what where I stopped for the break because I knew this was like, this is something you have to explain after the break rather than before the break. Right? So here's, oh no, I'm kidding. So here is what I do. Here is this boundary. I say, okay, I don't want to self-intersection false. No, interior should not, intersect with the interior of the other one. That would be overlap. But the boundary of this, of A, and the boundary of B have to have a line in common and not a point, right? That's what I'm saying here. And I call that function strrook. Yeah, so I create it on the fly and use it. Gives me the rook neighbors, and I can do the same thing with the queen neighbors if I would say here anything, yeah? True. That would be line or points. Yeah? And what I do here is that I say I want those neighbors for which they don't intersect with themselves, they don't intersect, they don't overlap, but they intersect in a point, right, where they have 0 dimension. And that's what I select here. So I select here counties that self-intersect in a point, right? And you get it here. And I was quite surprised, actually, when somebody, that was a GitHub issue, when somebody came with this data set and said, hey, I want to deselect a point. I said, point touches? I mean, we live in Europe, right? Tell me one place in Europe where we have like areas that touch in a point. I mean, point touches you get when you have a map and you draw lines, horizontal and vertical lines, and these are going to be the boundaries, right? It doesn't happen in this continent. This is, boundaries are here, the result of decades of, centuries of fights, really, and then long peace treaties and so on. And you never end up with, with 4 areas touching in a point. So that's quite cool. Yeah, cultural things. So here, and then I thought, how can I find these points? Because you see, this is a point, but this is not a point where 4 things intersect. Again, here is a point. So here is a little script where I say, okay, what do I do? Okay, I compute all the intersections, and then I say, well, intersections are areas or lines or points. Well, just select all the intersections for which the dimension is 0. That is the point intersections. Yeah, so these are these lines, and they're overplotted. There are 28 of them because they end up from every neighbor. They end up being an intersection point with with the opposite, the diagonal opposite neighbor. And you can use all these functions and dimensions and look at these things and find funny things in boundaries. Right? So this is a little bit more magic with these low-level geometric relationships and their dimensions and so on. Right? And here you see that that all these intersections of these points with the original data, they all intersect with 4 neighbors, right? So we see that again here. Yeah, then there's a lot of things, a lot of functions that here continue. That is sort of a bit of a list as the line merge. As if you have different lines, you want to combine them into connecting lines into single lines. These are kind of convenience functions more than anything else. Segmentize, kind of, if you have a long line, you want to put points on it, sort of have points in between them. Extremely helpful if you want to do graticules, right? You make straight lines in latitude, longitude, and you want to move them into some kind of projection. You need to do that with dense, you put dense points. If you don't do that, then it's all kind of goes weird everywhere. Yes? Segmentize just does it at regular distances, and it says you give I think you give the minimum distance. You give a distance, and the distance you end up with is guaranteed to be no more than that, probably less. So it does regular below a certain threshold. And I think that this is one of the functions where I do it properly both for longitude, latitude, and for Cartesian coordinates. So the longitude latitude will follow great circles instead of parallels, right? If you think 2D, you get the parallels, and if you think ellipsoid, you get a great circle. Yeah, the sort of when you have a rubber string and would pull it, it doesn't follow the parallels. Yeah, so I think this one again does that. Voronoi to the Voronoi triangulations. Centroid gives you the point centroids. Centroid is not always inside the polygon if you have like banana-shaped things, and also has no methods for longitude, latitude. Spatial. Convex hull, triangulate, finds triangles, but doesn't do it constrained. So if you again have a convex shape, it is triangles everywhere. The shape is destroyed. Polygonize takes a ring and makes a polygon out of it. Simplify does line simplification. Douglas Boyger probably, something like that. Splits, buffers, we saw that. Make valid is a function in the lightweight geometry post-GIS library, so that is not in the GEOS thing. That is an add-on, but I haven't seen much use of it, so fallback would be to buffer things with 0 buffer size. It seems to work too, often. And anyway, it is unclear what kind of the algorithm behind this really is. Boundary should return the boundary of geometries, if that means. Then there's a couple of maintenance functions, so to speak. The function st_zm allows you to throw out z or m or both, which tends to be quite convenient now and then. Z and m, you know, happen to occur sometimes, and more often than not, you want to get rid of them as soon as possible. Like a lot of shapefiles with contours come as 3D points, right? So you have a line string with x and y coordinates and an elevation, and they all have a z value because it is 3-dimensional data, right? But it's often not so convenient to work with that. ST geometry then retrieves a geometry column, which you could also do if you by name, if you know its name, and then ST lets you check on types and select or deselect types. Yes. Okay, so that was all for, let's say, the simple and the fun and GIS type things. Now we go into the messy things, right? The geometry collections, and empty geometries, which are the kind of the things that scare people away quite often for the wrong reasons. Yeah, so there's different options. One thing that we can have is a mix of geometries. Let me see. A mix of geometries, of geometry types for a single feature. Yeah, so the building consists of a polygon and a line for some reason. Because there's like a little road to the building that belongs to the property and it's represented as a line. Well, okay. So these things have been put into an object called a geometry collection. So a geometry collection can have anything in it except the geometry collection. In theory it could, but I wouldn't recommend. That's not recommended. Yeah, so you can have that. Here we created one with a point and a multipoint. So multipoint is just a feature that has potentially more than 1 point. And here it does, it has 2 points. And then we have a geometry collection. So why on earth, come people up with this geometry collection? Well, it has a reason, because if you do all the logic of the intersection things, you can pretty easily think of 2 geometries for which you want to have the intersection. So these are 2 nice polygons, right? It's just, if you want to have their intersection, you see that the intersection consists of a polygon, consists of a line string, and consists of a point. That's the intersection. And that is one geometry, right? So what is it? So that's a geometry collection, right? It ends up from doing the logic, basically. Yes, and it's a fact of life. And, you have to look at what kind of things ArcGeos had to do to deal with that, because the GEOS library simply gives you that. And then you need to think, okay, now I'm ArcGeos and I have these SP objects. What am I going to do with this, what shall I keep, what shall I throw away? So there might be all kind of funny things that accommodate to that. It will select, of course, one of these things. And in SF, you nicely get back a geometry collection because it's part of the language and of the class sets. Yes. No, if you have like two geometries, A and B, A is red, B is black, then the intersection, C, is all this green stuff. The point, the line, and the polygon. No, there's no mirror of the top one. Yeah, so, yeah, right. The intersection of A with B and the intersection of B with A. Yes. And the intersection of A with itself and B with itself. Yeah, you would end up with 4 intersections if you use anti-intersect on the set of these two geometries. If you would use ST-intersect on one geometry and on the other geometry, you would just end up with the green stuff. Yeah, because ST geometry can take geometry sets, and the set can also have size 1. Yeah, it can be red, ST intersects, red, black. Then answer is green. Yeah, it's different ways. It's tricky, but it works. Right. So you end up with it's ST geometry collection, and these things are real and happen. Right. We can also have, like, at a feature level, so at the level of feature sets, so of SF objects, have different objects that have a single type, but that are of mixed type. Yeah. So one feature has type point, another feature has type multipoint, another feature has type line string, and they're a mix. They're single typed features, but they come together in one table, right? So what's the type of the table? So it doesn't have a type, so it has the supertype called geometry. So that's something else. It's not a type, it's kind of a type, supertype. Yeah? Of what is it? How do they call it? Supertype? Yeah, so these happen to, and then what are you going to do with them? Well, there's different things you can do. Of course, you can look at, okay, what do you have? What are your dimensions? Oh, your dimensions are 0, 0, and 1. Yes, because I have a point. Multipoint also has dimension 0 because it's a point set. And line string, of course, has dimension 1. Right, so you can, in that sense, select on you can select on types, on dimensions here, and you could also select on type and say use st_is and you select on type. There is also another function called st_cast that tries to be, whether it's helpful or not, it tries to be helpful in going from one type to the other. For instance, a thing that quite often happens is that you have polygons and multi-polygon mixes, which is also a geometry. You know, they're mixed. But typical administrative data, boundary data, are kind of come as these mixes. Here you see all the counties have one ring, the normal counties, and then the ones on the coast have several rings, right? The mainland and a couple of islands. So this is more often than not. So already the st_read or read_sf functions are in that sense convenience. Whenever you have something of type and multi-type, yeah, so point to multi-point or polygon and multi-polygon, it will convert by default the whole thing to multi-polygon because that includes polygons as a special case, and that is more convenient, yes, to have. And for instance, yeah. But then sometimes you end up with these combinations, and then stcast, I think if you don't say anything to stcast, then it will try to find the simplest kind of superset, so it will convert things into multipoints. But here I had also a line string, but line string can of course be converted into multipoint. So if I make this a multipoint, it will make this a multipoint, and then you have a line string converted into, which is of course a completely different thing. But hey, this might be convenient, and this is R, so there are no rules, right? So anything we want to do. Yeah, it converts line strings to multipolygon. They're the same representation, they're point sets, so it is not an issue in that sense, just a type conversion. Also stcast without arguments, here the argument is this whole object, so I don't specify what my end type will be. Stcast tries to unravel geometry collections, so cut them up in parts by duplicating the attributes and basically giving the subparts as geometries. Yeah, so for in case that is convenient, right? Because you can of course do this by hand, by nested LPLIs or something like that, or per statements. But it takes some time before you get to sort of before it works nicely with all these nested lists. So this might sometimes be helpful. So if anything's nasty happening, throw things in SDKs and see what happens. It might resolve something, maybe not. Last thing that is sort of a nice property of the simple features kind of world is that of empty geometries, and they're basically the empty set, right? So it's a point but no point, right? So it's the non-existing point, yes? And they are you can think of them as NA when you had like a vector with numeric values, or you can think of them as null if you have a list, right? The null object is the null object. You can have a list with nulls. But they're not. They are typed. Yes, they are sort of, you have a typed empty point or a typed empty geometry. And for the geometries and so on, this works nicely because they are lists. They can be empty sets. For the points, this doesn't work so nicely. And this is seems to be a flaw in the simple feature standard now recognized 10 or 15 years after the fact, that points have at least 2 coordinates and empty points don't have 0 coordinates. It's like they still have 2 coordinates. So the statement to create an empty point here basically generates a point with 2 NA values. So the well-known binary representation of that is also not sort of something without coordinates. It's something with coordinates. And then, well, what do you do? Put NA values there, right? So this is an implementation detail or a design flaw or whatever you could call it, but I don't know. But so for most things, almost anything else, they are sets or matrices. Matrices can have 0 rows, no problem. Lists can have length 0, empty lists, and so no problem. So all of these things work. And the thing to filter them is, you sometimes end up with them. The thing to filter them is to use ST dimension, and it will give NA when I have an empty geometry, and then you can do is NA on the dimension of the geometries, and you see which ones are empty. You don't end up with them that often. For instance, ST intersection, you will end up with when you do an intersection of 2 non-overlapping polygons, right? That would be an empty set. And of course, ST intersects give you the Boolean or the index of things that intersect. So things that not intersect are not there, or they are false in the dense matrix. And ST intersection just gives you the non-empty intersections, gives you the non-empty geometries. So if you do 2 large data sets and intersect everything with everything, then almost everything will be empty. So you don't want to have a huge, massive amount of empty things. By the way, also discovered by a GitHub user that said, hey, why do you do that? And it was pretty much a revelation to sort of do that, check that at a much more lower level. In the same, that was, I think, mentioned in the same blog on the spatial indexes, which mentions, this was kind of raised in another issue where memory usage exploded for some reason, and we could bring that down with like a factor 10 or 20. Anyway, it's good to sort of be able to ignore them. Where are my slides? To ignore them, and most of the time they don't appear, right? You don't want to sort of know about it, but sometimes they do appear, and things are. And in particular, if you do joins, right? If you do a full join or a left join, you want to have, and you do that with ST join, so spatial joins. You want to have for all the records of your first table the matching records of the second table. If the second table doesn't have matches and you want to give the geometry of that, then you end up with empty geometries. So it is not like there are no cases where you don't want that. So for all the niceties that SF offers, now a little bit about the PI-based workflows and the tidyverse. And then I will sort of give a little bit more of an looking back and an outlook of things. So here is a little use case where I try to, yes, this is so package SF has all these methods. Here is this whole list that you basically only see them printed as methods after you have loaded tidyverse. Essentially, dplyr and tidyr are the things where these verbs are, where their generic is being defined, and then there's like a long list of things with underscores when this is about dplyr 050, or without underscore when this is about dplyr 070, the new one. These things change, randomly, not completely randomly. It's announced, but and so as I mentioned earlier, if you throw your things into a dplyr, what you get back is a tibble, and that's it. That is one thing. Yeah. So the object lost its information about which column was geometry, which might not be a drama. It's okay for some. Another thing that happens if you do joins with dplyr, it uses its own methods to do selections on list columns. Yeah, so if you do a join and you have to add in NAs, it puts nulls in the list column. Whereas simple features would say, no, I want to have an empty geometry. We just learned that, right? So this is like dplyr does this thing, although SF has a square bracket method for list columns. It, whenever things are in deep in C++, it's not always, there's no, method dispatch is not sort of the most obvious thing. So there's some kind of, some kind of correction cycles that need to be done then when things come back from dplyr into sort of get them back into the simple feature verse, so to speak. Those are basically these methods. So most of these methods really do nothing. Yeah, they just say, okay, use next method, and then clean up the mess. Sort of correct the things that dplyr thought was good to do. Take care. And some of them actually do something, and that is already what I mentioned. That is, I think, mostly summarize. Yeah, and maybe only summarize. And yeah, okay. Maybe there is more logic. It was a while ago that it was there. So here is an example of a pipe-based workflow. I'm not sort of, this is not the area where I really feel at home, but it seems to work. What I do here is I take the geometry, the list column of my states object. I compute centroids, so that gives me, instead of polygons, gives me points. So simple feature points column. And I take the coordinates from the ST coordinates, puts that into a matrix, because that is sometimes convenient. And then I save this matrix. Now matrices are, of course, very much anti-tidyverse, but I didn't know another way of doing this. But anyway, here are the longitudes, latitudes, right? Logic is always x, y, longitude, latitude. So then I go through my states again and say, well, mutate them, and that means add a column that is called area, and that is computed by ST area, so that gives me the square meters, which then breaks all kind of other things in computations down in dplyr. So I had to sort of convert them to numeric, meaning dropping the measurement units. Otherwise, I get sort of, packages don't like each other problems. And so we get areas. Then I say add a column called longitude and take for that the second column of these centroids, right? Longitude, first column, longitude, latitude, right? Take the first column of the centroids. And then I'm going to group, and pipe this whole thing into a group by. And group by, I'm going to cut longitudes into 4 pieces. You see the pieces on the map already. So I get 4 areas, so tuk from east to west. And then I'm going to summarize that and compute a new variable for each of these 4 areas called area, which is the sum of the area. Makes sense to sum areas, right? It's very, very extensive, the variable. It's a very extensive variable, area sum. Compute the new birth rates, also by summing the, not birth rates, well, the yearly birth rates, but birth numbers from 1979 as the sum of them, and compute a new variable that is the mean of these summed birth values over the area, which was computed here. So this is the nice thing, or well, nice or confusing, whatever you think, that whenever you compute here something, that this is the thing that is used here and not this one. Maybe it is bad style from my side that I use the same name for both, and it would be clearer if I would use other symbols, other names or so. But I think that when I use area here, that it's actually this one that's being used and not this one. And I'm not even sure. I should check. Because I think one is right and the other one is not right. So I'm starting to doubt. I used my students in my spatial data with, spatial data science with R class as guinea pigs for this tutorial. And I completely got lost here. Like, is this right? Is this wrong? I wish they could help me. It's tricky. So I need to look into this. I agree with that. And then I used ggplot on this final object that you see here, which is the sort of the counties cut in 4 longitude classes, with the geom SF that nicely then uses the dense variable that they defined here as the color sort of thing, and gives me these 4 areas. And you see that by default, as I mentioned earlier, summarize resolves these internal boundaries. And luckily, these are sort of regions that belong together, so they are kind of clear that this is the region. If I would use another criterion to group these counties, you would of course get sums that are values for different polygons, and you can't see anymore for which region they really apply, right? We got this problem in a blog post earlier this week, where somebody very enthusiastically said, "Oh, yeah, polygons," and then it's very easy to get very much meaningful choroplate maps actually because we tend to read things different than they are, especially if we plot amounts as the color in them. That's why I plotted densities, but still I don't know if they're right. And again, you see the sort of the nice curved graticules on the background that I'm so happy with. Right. So it was actually what I wanted to talk about long enough about a simple features package so far. And are there any questions to this last section on the dimensionally extended 9 intersection model or the tidyverse pipes? Yes? That is a good question. Are there any plans to improve the synergy between SF and data table? Could you say a little bit about the current synergy? Is there anything? Mm-hmm. Aha. So I'm using data table and I keep going back and forth between formats. Okay. Probably it's a bad habit. I'm just wondering. Yeah, and for me it's right now a question whether this is a problem caused by data table or whether this is a problem with the current geom_SF. Because I think that, at least my experience is that geom_SF right now requires that the geometry column is called geometry and cannot have another name. I think this is still an open issue with ggplot. So that might be also the issue that you ran into. So I'm not very familiar with data tables. I know some people who use it, and I'm sort of happy to hear experiences and to learn whatever we can do. The idea is that, let's say, the ST-SF method that creates these SF things basically creates them by augmenting the classes what it gets. So if you give it a tibble, it will make it an SF tibble, etc. Tibble has like 3 classes. If you give it a data frame, it makes an SF data frame, and then removes it later on and so on, keeping the class attribute as such. And in principle, data tables are data frames, right? I mean, they sort of subclass data frames, but that is the same discussion with table. It's messy. It's very informal, and some things work, some things don't. This is S3. It's Wild West. You know, there was a good time that we were in S4. And this is quite nice. No, I don't want to open a can of worms. There was another question. Yeah, where was it? No, okay. Yeah. Yeah, so there are spatial models like the things in SPDEP, like neighborhood models and so on, the SAR and error models. And then there's also the geographically weighted regression models, where I think the sort of the spatial statistics community said, you know, interesting, exploratory, but try at your own risk or so. Yeah. SPDEP uses these NB objects for neighborhood lists that are essentially the same things you get back here, but have a class and have a couple of attributes. So I was planning to sit together with Roger Bivand and see whether it makes sense to either write a converter or to make the sparse indexes that are returned by these functions compatible with the things that are being used by SPDEP. SPDEP does basically just reads a data frame with attributes and a neighborhood list. That's it. So, or a neighborhood weights list. It has also these weights, like neighborhood weights. Yeah, but it doesn't need polygons or so. Yeah, it needs polygons later on to plot things, but not for the computation. They just use like what is a neighbor with what, or which one does have like a weight in the spatial weighting thing. So these are objects that are pretty much compatible with what we have here in terms of information. It's just in whether there are attributes and classes, like, okay, my indexes don't have like the number of columns, the number of attributes there could be in, right? Addressed this week. Any other questions right now? Yes, Tom?
So RGDL leads the things to the SP classes.
Yes.
So
No, that's not going to change. No. No, so this is the migration path is that SF is the new RGDAL for SF objects. SF is a new SF replaces SP, RGDAL, and RGOs.
So that the RGDL will be slowly phased out.
RGDAL will do things with SP classes. Yeah, well, phased out, that is sort of looking into the future and discussing whether the 400 packages directly depending on SP will all migrate. I think many of them will never migrate, which, you know, it's good or bad. I don't know how much they're used. I mean, I'm not sort of writing emails to the maintainers of all these packages like, hey, you need to do something or so.
Is there anything which is lost in SF?
Yeah, we discussed that a little bit in the first hour. SF is basically a superset. So when you go to SP, you might lose some information. Things like empty geometries are not in SP. Geometry collections also not. Mixed sets, geometry are not there. And difference between polygon and multi-polygon are not there. So when you do a round trip, you might have lost something, but not really essential information. Suddenly all your polygons are multi-polygons of length 1, who cares, right? So it's not like really information is lost. At least there are not that many cases in which you will have like losing significant information. But there might be cases where that, of course, that you can construct where this loss is important. When empty sets, empty geometries are important for some reason, then you can do it only with SF. Yeah? Last question.
Yes. Some examples where it's like parallel computing to do something.
No. No. None. Just do it. Just throw things in for each or so, or in whatever packages to do that for you. I don't see any problems there. Most of these packages replicate your data, and so if you have a large intersection problem and you want to do that over 4 or over 64 cores, cut something in 64 and do it or so, and join the results. I think. Didn't try.
Well, I mean,
That's what I would try first.
for us, this would be that it's automatic. You just ask how many cores you have, and automatically.
Yeah, but I don't think this is so hard, right? And it is sort of doing a lot of automatic parallelization kind of, might backfire. Yeah. So if you want to, if you do something in loop and you already want to parallelize your matrix inversion or so, you don't want to also parallelize over your iteration over your features, right? Because then you you cut yourself. So I see that as basically as a user problem, yes, or a thing that users should try first and take care of. If you have data size is that large and computers that strong and so on, you know how to do it. Yeah. But yeah, it would be nice. But then we're not writing a GIS or so. It's like okay. So are there any further questions? Follow-up questions on this? Yes, just to make sure. Good. Okay, then there is the recurring question, like how will this sort of interact with the raster package, right? We have now SP. SP has a couple of classes for gridded data all in memory, which we do little problems. But then there's a raster package, which is a massive, large package, where Robert Heijman spent 10 of his best years on programming, and that does solves a lot of problem with raster data. So imagery data, digital elevation models, whatever. Lots of land use. A lot of spatial data are basically handled by regular spatial discretization, leading to raster maps, and raster can deal with raster maps and series of raster maps of different features or time series. And basically does that by saying, well, these things are all on disk, and tell me where they are, and I will take care of anything else, right? So that is a very nice setup, because these data are quite often too large to be reasonably handled in memory, and that is what raster does. So raster solves sort of a large problem for many people, because it iterates and it can do like prediction models. So if you want to sort of quickly develop a random forest prediction model on land use, to forecast land use based on remote sensing imagery, it's not so difficult. You simply use the random forest package and integrate these things, right? So in other environments, this would be much harder to do. Robert has so far not responded to such queries, and he is sort of less actively developing the last half year than he was before. So he might simply wait and see what happens. And so the only option you now have is basically, do you think, convert them to SP, do your raster integration, convert back to SF, or use other packages that are, I think Andy has a packages, right? Rasterize or something like that. There are other packages that do particular raster operations that might interact with simple features, like rasterizing a polygon data set or something like that. So there are also alternatives to some of the functionality of rasters. So there is right now not a migration plan, and this is of course true for raster and true for the other 400 packages that use SP classes as well, right? Some of them migrate and some might not, and it is basically we can't help that. Yes, of course there's also me, and I'm responsible for a couple packages like the package GStat, and package GStat does geostatistical modeling, variogram modeling, and then Kriging interpolation, these kind of things. And you typically do that to a raster, right? So you have points, do variogram, and then interpolate to a raster. So I'm not going to migrate that so long as the input data would be as simple features, and then the output data would be like a raster or a spatial grid data frame. I'm not going to sort of mix these frameworks or so too much. This is not really worth the effort. So we have to look at where raster is going, or where raster computing is going. And it is basically also what I will talk about which is in the GIS session tomorrow afternoon. There is a follow-up project called STARS that stands for, let me see if it is here in my slides. Yeah, there is a package called STARS, it's mentioned here at the end, that stands for Spatiotemporal Tidy Arrays for R. And this is sort of a next project after Simple Features that I will be working on together with Michael Sumner and with Etienne Racine. Michael from Australia and Etienne from Canada. This is also an R consortium supported project, and that so let's say that includes raster as a special case, but it also looks a little bit further. It looks at arrays in general, so also a time series. So the same thing is true if you have a time series for each feature, for each county you have a time series. How are you going to store that? Right now, these days you can think of nested tables, right? Who of you has worked with nested tables? Yeah, see, it's happening, yeah. But if you have nested tables, right, you have basically you would have a geometry column. For every county, you would have a table with a time series. But then the question is, are these like the same time series, right? It's not a table. They're each of them is a time series. So the next thing is you want to do something with the time series, and the question pops up, are they aligned, right? Are they the same time, extent and intervals and so on? So that is not, like nesting is not an option there. So you really want to look at arrays where basically along one array dimension you have the spatial features, the states or the counties, and along another you have the times, or vice versa. But two-dimensional data really is the thing there that you need to. So that is where the array word comes from. Simple feature tables are one-dimensional arrays. And anything that is more than one-dimensional is gonna, you have to, tidy would say, I'm gonna replicate everything, or nest, but it isn't messy. Yeah, so you need to work with dimensions, with arrays there. And this project actually has ambitions that go much further than that, not just generic array, where array dimensions refer to space and or time, but also to deal with a case where I have raster data, and the raster data no longer fit on my local hard drive. But for instance, the raster data are in the Amazon cloud or something like that. So this is the more sort of realistic proposition for today's raster data. The sizes of the data are no longer realistically downloadable. Yeah? So that is what raster does. Raster solves a problem as long as it fits on your local hard drive or drives. Yeah, and that's not, that is quite a few problems, but not all the problems. Increasingly less problems, I would say. So there's a few sort of summary or concluding statements or outlook statements. The comparison of SP and SF that we have now, basically SF summarizing implements all types and classes of simple features. Those are clearly more than SP. SP has to, make all twists and things whenever the result of a query is a geometry collection and it has no clue what to do with it. Here it's clean, empty geometries and things. That is nice. It has no support at all for gridded raster data. The example I showed is basically doing square polygons in a regular grid, yeah, which is of course fine for coarse rasters, right? It's not fine for large geometry data. The SF classes really use data frames, so they really are data frames. They are lists of equally length columns. Uses list columns, which is a very nice thing for feature geometries. Without list columns being sort of handled reasonably, there was no way of doing this properly. And it uses, as opposed to SP, it uses S3 instead of S4. And that has all kind of nice sides, and it has all kind of, you know, itchy sides or so to it. Yeah, but it's okay. You need to communicate a lot with other package maintainers, which is fun and usually goes very friendly and supportive. And it's also built on top of GDAL, GEOS, and Proj 4, like the SP verse, like SP and RGDAL and RGEOS did, still do, and in the near future, both will be supported, I think. Yeah, Roger does GDAL and RGEOS, and I do SF, and we are in touch a lot, right? If there are issues, we solve them, we inform each other. So issues are there always, if you're not aware, packages that have external dependencies in terms of external libraries that need to be linked. Installing them on cron means that all the cron testing platforms need to have these libraries installed on all their platforms. That is one thing, and that it needs to pass check on all these platforms. So if new versions come out, right, you need to convince all kind of people everywhere that they should update or not. And that is one thing. Another thing is that Windows and Mac binaries are compiled by cron and are compiled using statically linked libraries. So if you install SF for your Mac OS operating system from cron in binary form, you download a package of 100 megabytes. Yes, that includes a complete binary of GDAL and GEOS and Proj 4. That is why it's so large. And GDAL is really a library of libraries. It links to like 20, 30, or 50 on my computer, 80 other libraries, because it supports, you know, all the craziest data formats on Earth. So it's kind of a meta library that is, you know, useful, but it's complicated software. So this is like doing this in a relatively sustainable way. It takes a lot of effort and a lot of communication efforts with the people from cron, with Simon and Brian, and with Kurt and Uwe and so on, who are, by the way, extremely helpful and patient, as usual. It's an effort. And what SF tries to do is basically provide a simpler and cleaner API or user experience, whatever you want to call it. And conversions to and from SP make it still pretty easy to work backwards, to work with both environments. Yeah, so there's not like I don't see big issues. People don't like it, of course. They want to have everything with SF working, yes. Well, then you need to convert things. So what is now really new and better in SF compared to SP? We have simple features. It's a widely adopted standard that is everywhere and can map that into R and go back without loss of information. So we have clean round trips. SP would not do clean round trips. You load things into SP and do it back, and it might be clean or not. You don't know, because it's a subset. It's tidyverse compatible, so that you can all do all kind of things, although a lot of things already worked with SP functions as well. It has ggplot2 support, which is still, you know, there are still issues around that, but that we're working on that. So we did a lot of work at the beginning of this year, and I think Hadley is putting his head around new ggplot release. We'll do that soon, and then we have to address a couple of remaining issues. Like, for instance, plotting spatial points with geom SF, I think, is still pretty shaky. Everyone tends to think polygons is like all we need, right? But it's, you know, it's not all there is. There is a nice support for measurement units. In the units package is self-advertising, but it's an extremely nice package that makes it very easy to basically do all kind of meaningful computations on units. It does automatic unit conversion. It does sort of checking. It checks you when you say, okay, now add some meters to seconds. It will say, no, you can't do this. So it is a very nice package. And units are in these coordinate reference systems. So we can actually do that. And you can sort of pass, you say buffer and give the buffer distance in kilometers or so. Yeah, it's very nice. There are partial support for computations using geographical coordinates. There is a very nice support of things that I didn't completely ignore, because my assumption was that this morning was a lot about mapping. So the packages MapView, TMap, and MapEdit. MapView and TMap are extremely good visualization packages. Both have an interactive version like Leaflet, interactive map plots. MapEdit lets you even edit. This is a very new package that Tim sort of supervised and that he wrote together with Kent Russell, that lets you edit features, basically move single points and so on. SF has now 15 reverse dependencies on cron, and then you have to acknowledge that it's only sort of usable since like 4 or 5 months, so that is kind of quite nice, fast pickup. There are binary geometry ops that are now indexed, and that makes and have a lower memory footprint. The memory footprint and the slow versions are still in ArcGeos. So if you do like geometrical operations on larger data sets with SP and friends and compare that with SF and friends, there's no returning back. I will promise that. This is sort of order complexity is a thing that you can't beat. It's not something that I just started using the function. Somebody else implemented all these things, really. It has a very clean interface that uses RCPP. So just have a look at the code bases of ArcGeos and ArcGDAL. And in all respect, I mean, this happens when you maintain software over 15 years that links to libraries that change over time, and you have all these versions things, and you just need to have a 5-minute look at the code, and you understand why we want to migrate and want to migrate sort of drastically, in the sense of not modify code, but rewrite code. Using RCPP kind of made things also extremely more lean and efficient. That is, I can recommend it to everyone. I would never turn back to using the C.call interface. This is just sort of too good. And it has very fast, well-known binary writing and reading, and it makes it extremely simple to interface to all the other libraries, because all other libraries can read and write well-known binary as well, because that's a standard. So you have never problem of getting your data in and out of other environments like GDAL, GEOS, or other libraries that are still to come. Still to do, as I said, is the geom-SF thing in ggplot2. Geographic coordinates. I look forward to Ege's talk tomorrow in the GIS session. We can work with geographic coordinates, but we don't have spatial indexes for them, right? All the spatial indexes that GEOS offers is all two-dimensional, and there are solutions for spherical coordinates, so that is something to look at. As I mentioned, time series for simple features are not there. Raster data, raster time series, raster simple features integration are all part of the STARS project that is going to that is really in the design phase. Interestingly, that is exactly in the same phase as simple features was exactly 1 year ago when I gave this talk at the useR conference in Stanford about simple features, with this kind of vague ideas and sort of raw design, wild ideas, and then suddenly it was there. It's fun. What we still need to do, or what we still might want to do and think about, is to scale from in-memory to in-database operations, right? So as I said, you can think of simple features, the R package, as kind of as a mini in-memory post-GIS that uses R syntax, which sounds very nice. It is very nice, it's fast, but until the moment that your data no longer fit in memory, then you need to think. So if you have really like a billion small polygons, take a reasonable section of OpenStreetMaps. It doesn't have to be a large area, and it blows, it blows everything up. So there's just so incredibly much spatial data. If you want to work with data of that size, really you need to think of putting them in a database and having the database doing things. And dplyr does these things pretty well with tables and relations between tables and so on. And it would be quite cool, and it might be a future R consortium project that I just discussed with Kirill over the coffee break, to integrate that and to have proxy objects to spatial databases and have sort of pipe-based workflows being translated into SQL without you having to wonder how these things are being solved. Right? That would be quite cool, but also a little bit of work to do. Yeah, so I'm a little bit early. I think I still have half an hour or so, but I'm sort of through my slides and through my voice. So I would say thank you. Well, that's great. Thank you very much. Are there any questions that we still want to, there is time that we want to address? Or particular issues somebody wants to bring up or discuss in a wider setting of this tutorial? Yes?
Do you see, I'm coming from geography and, you know, we have S3, ArcGIS,
Ah.
QGIS, doing our studies. Do you see a way, like a tendence that R can replace such traditional GIS systems?
That is a very good question. So the question is, there is S3 ArcGIS, the Microsoft Windows under the GIS, and there is Quantum GIS, the Linux under the interactive GIS environment. And would R eventually, possibly, replace something like that? I never see, sorry?
Please say yes.
Oh, yes. Well, yes, no. I tend to say no. I tend to think there is not just R, there is also Python. And Python, if you look at Earth observation, 90% of the people use Python. That has reasons. Yes, that is also GIS, but they use Python, not R. Yeah? So there are. It's more complicated. I'm kind of more tend to think like, yeah, there is open source and non-open source. I tend to less and less interfere with the non-open source because I'm not so much interested in that. But of course, you need to look at what's happening in the world. Then there is GIS, like Quantum GIS R. I tend to tell my PhD students that if they do all kind of things with Quantum GIS, that I can't see what they've done, right? So it might help them. It is like, you know, initially you do things just by, if it's easy, and then later on you want to redo it in some environment that where you can see the recipe, you can redo it, you can see the script. Otherwise, it's no science. You can't write down mouse clicks or so. So it's good. It's helpful, yeah, but it has its limitations in the sense of communicating what you did, and I'm not convinced it's enough. Yes, it's a stage, and you want to, when the stage has settled what the workflow is, you want to sort of write it down in either Python or R or something like that. And you know, R is then the thing that I'm familiar with. Yeah, so I think that for proper science, you need to, where you can, you need to avoid interactive environments and also avoid closed source solutions. Just, yeah, for science. But of course, if you're an engineer and you want to sort of, you know, design a park or something like that, then I don't know why that should be reproducible. Yes, that is fine. So it has its place. But for science, it's a more difficult proposition for me. Yeah.
But there's another part of traditional GIS, for example, for utilities. People using GIS not for science, but for updating maps or utility maps.
Yeah.
I mean, and with stuff like map edit, that might become possible.
Yeah. Yes and no. It's not so easy to replace. They're quite. It's also quite organizations with people who've used a particular solution for 10 or 20 years that are not incredibly enthusiastic to do that with things that are completely new or so, right, and that are kind of change every few weeks. So there's this organization problem. As I said, I have nothing against engineering environments where a particular closed source software simply solves the problem. What I found interesting is that the people who are now have taken up Project 4 to improve that further for a number of requirements, they were from the Danish cadastre. And they said, well, we've done all the time this with commercial software. We want to move this whole thing to open source software so that everyone can understand what we do and that we can understand it ourselves. And that takes an effort, but it's good for everyone that they take that effort. And this is an institution, a cadastre, right? And that is, you know, that's a nice development. So yeah, there are changes somewhere that are hopeful, and we're doing things. Yeah. Yes.
So, like in Python, when you stack a large amount of clusters, you use NumPy.
Yeah.
Operation.
Mm-hmm.
So at the moment,
Uh, I don't know exactly what NumPy does and doesn't, but indeed many people use that, and it's very powerful, and of course it doesn't know anything about spatial references. And sort of half of the joy of working with software is that it takes care of spatial references, that you don't lose that and have to add it again. Like you start off with throwing away your measurements units, and later on you have to add them again to the plots, right? That's not what you want, right? You don't want that. It's simple, you want to have things passed on in your workflow. And so plop, you say, oh, map. And no, NumPy just gives you a PNG, non-georeferenced. That's what comes out. You have to put the things back. Yeah? So it can be very powerful, and apparently people don't care that, or the benefits of using NumPy are so much larger than the disadvantages. Yeah. Yes?
Functions in SF, can they replace the functionality of GRASS?
You would replace functions in SF with functions in GRASS. Yes. Yeah, well, that is... well, this is kind of hooks on the last option I said here, where I was thinking spatial databases, like PostGIS, but you can also think of a GRASS backend, and then have proxy objects in R that kind of know where the data is, but they don't try to represent everything in memory. Yeah? So that would be, you could think of a GIS backend to, you would subclass these things and work with proxies and then defer expensive operations to GRASS, who scales that, who does a proper scaling and on disk and has indexes and so on. Disk-based indexes rather than on-the-fly computed and discarded indexes, what SF now does. Yeah. Yeah, that's a good idea. Yes?
In this start memory, do you plan also to integrate trajectory data?
No, actually not. No. No, very much not. So because trajectories are sequences, are one-dimensional arrays, we are particularly looking at dense multidimensional arrays. So that's a particular kind of data that is not trajectories. But of course, trajectories are also interested, but you could represent them pretty well in simple feature tables, and you could then interact with them with stars object, like what was the temperature of water where the dolphin was, or something like that, right? So you can intersect these things, but no, I would sort of go for trajectories. My first shot would be nested SF. Tables with nested SF objects, where each SF object is like a track, like is a sequence of GPS readings over a particular time frame, because anyway they're different in times and space and so on. And yeah, that would be my first shot to representing trajectories, which you can already do, but you don't have very much convenience functions right now. But the integration with SF I have in mind to do with stars, right? So I am also thinking of time series of features, for instance, or how would you represent a discrete global grid, right? Which is these hexagon things, like grids that are not regular, rectangular, square grid cells, these kind of things. That should also be possible. Good. Okay. Oh, last question. What about it? I told it last year in the tutorial. You should have come. I talked about the space-time and the trajectories packages. Yes. Let's say the idea of stars is multidimensional arrays with space and time references. That is basically what STFDFs also do. But STFDFs, space-time full data frames, live in memory. Yes, and stars object will, from the start of, not assume that everything is in memory, will be held in memory. Yeah, it's not dissimilar. The ideas, of course, are similar. Yeah. Okay, so let's call it a day. Thanks everyone for attending.